Hey, AP Chem, I'm going to go through the last couple practices in chapter 14, mostly about dealing with salts as acids and bases. Okay, so this is the first question. Let me move myself. So good time to pause the video, time yourself for a minute and a half, see how far you get. All right, so as we read through, we're going to underline information. So we're going to pick a species with the lowest concentration. All right, sodium, HPO42 minus, H2PO4 minus, PO43 minus. Okay, so some of the concentration information they give to us in this initial information up here, they also give us some information here. So as far as sodium goes, sodium's going to come from this first solution here, 0.05 liters times 1 molar. Remember, liters times moles over liters is equal to moles. So if I'm going to compare them all in moles, now I get some from the first. I also get some from the second one. So in this one, I'll have, let's see, same volume, same concentration, but there's 2 sodiums in there. So quite a lot of sodium. Okay, now H2PO4 minus, so we get this 0.02 liters times 1 molar concentration. Now it is going to proceed forward probably, but not very much. So minus X, if we were to set this up in an ice chart with our weak acid going to our hydrogen, if this has a specific amount that we start with, our change, since it's a weak acid, will be an X. So our equilibrium position will be whatever our initial concentration is minus that X. And remember, usually when things have a very low Ka, we can kind of ignore that X. So this solution is going to be really close to what it is initially, maybe minus a tiny bit. Okay. And we don't have any of this first reaction. We don't have any H3PO4. That could be another source of H2PO4 for us, but we don't have any H3PO4. So we can kind of ignore that. All right, HPO42 minus, same concentration, same molarity. Now, again, we're going to be minus a change here. So whatever, let's just call that change Y, since we have X on the table above us. You're also going to form a little bit here, so plus X. Okay, and now PO43 minus is just going to be equal to that change that you get from the ice chart. So I really don't have to do any calculations. The answer is going to be D. Sodium is going to have the most by far. H2PO4 and minus and H2PO42 minus are really going to be governed mostly by what they start with. Their concentrations are going to be very close to what they start with. PO43 minus is the only one that's going to be dependent on the change by a super small Ka. So that change is going to be really small. So your answer is going to be D. Now that's a lot of processing. Hopefully you don't have to write out as much as I did. I wrote that out so that you could see the logical process that I went through, but hopefully you can do a lot of that in your head. Because if you did have to write it out, it would take you a while. Okay, let's go find the next practice problem. All right. So here we go. Problems with salts. Calculate the pH of a 0.3 molar. Oops, I'm going to calculate pH. 0.3 molar NaF solution, and then they give you the Ka value. Okay, again, good time to pause, work it through, see how far you get. So I want pH. I'm going to have to get to H plus concentration. So NaF is going to be a soluble salt. It's going to split into Na plus and F minus. Now, Na plus is the conjugate of a strong base. It's going to be a useless acid, so I can ignore it unless it's convenient to me. F minus is the conjugate of HF. HF is a weak acid, so F minus is going to be a weak base. So I need the reaction with F minus. Now they give me a Ka. If I can write this reaction one of two ways. F minus plus H2O goes to HF plus OH minus. I could also write it as HF dissociating into H plus and F minus. Now, if I do it this way with the Ka, I have a 0.3 here and a 0 and a 0. If I do it here, I have a 0.3 here and a 0 and a 0. So writing it with the base, with the equation as F minus as the base, kind of makes a little bit more sense to me, but that means we're going to need the Kb instead of using the Ka. So Kw is equal to Ka times Kb. So to find the Kb, I take Kw and divide it by the Ka. And then I get the Kb, which is equal to HF, OH minus, F minus, which is, if I plug in my equilibrium positions here, I get 8x squared over 0.3 minus x. I'm going to ignore any x's that are added or subtracted, so I get x squared over 0.3. All right, so let's figure out what these things are. First, let's find what Kb is. So I'm taking Kw divided by Ka, and I get Kb. So my Kb is 1.3889 times 10 to the 11, negative 11. That's a small Kb. Okay, times 0.3, square root of that. My x is going to be equal to 2.04 times 10 to the negative 6. And that x is my OH minus concentration. So if I take the negative log of that, I get the POH, which is 5.69. If I take 14 minus that, I get the pH, which is 8.3. How many sig figs do I keep? 2. 8.3. Jenna, there we go. Okay. Did you get the same answer as I got? Where did you get stuck? What questions do you have? It is a little tricky here trying to figure out which way you're going to write the equation. That's worth practicing. Also, switching between Ka and Kb is also worthwhile to practice. Let's look for another practice on salt. Okay, similar question. They're looking for pH again. They give you a concentration of an NH4Cl solution. They give you a Kb for NH3. Okay, so step 1, pause the video and try it yourself. Step 2, figure out what's actually going to affect the pH, right? So we have an NH4 plus and we have a Cl minus. Now those are the two things in solution because this is a soluble salt. It's going to fall apart into water and I'm going to have two ions affecting the pH, not one molecule, right? Okay, so NH4 plus is the conjugate of NH3. That's going to be a weak acid that will affect our pH. Cl minus is the conjugate of HCl. HCl is a strong acid, making Cl minus a useless base. So that will not affect the pH. I can ignore it if I want to. Again, we can write this two ways. We can write NH4 plus as an acid, resulting in something like this. Or we can write NH3 as a base, resulting in something like this. Okay, now if I plug in the information I have 0.1, I can ignore anything that's a liquid. 0.1, ignore anything that's a liquid. 0, 0, 0, 0. Okay, so which one's cleaner? Remember, the next thing we have to decide is which way the reaction is going to go. This one clearly goes in this direction. This one, if I plug in the Q, 0.1 times 0 over 0, I have a 0 in the denominator. It's definitely not as clean of a calculation. So I'm going to go with the first one, which is an acid equation, meaning I need a Ka. Let's fill in the ice chart before we deal with Ka. Negative X plus X. It's a weak acid, so our change is going to be an X. Okay, so a Ka is going to be Kw divided by Kb equals Ka. Let's figure out what that is. So we take Kw, divide it by Kb. That's our Ka. So our Ka is going to be equal to 5.56-ish times 10 to the 10, negative 10. All right, so Ka from my reaction will be my hydronium, my NH3 over my ammonium. Okay, if I take my equilibrium positions and plug them into my K equation, I get this. I'm going to ignore X's that are added or subtracted. Okay, so I take my Ka times 0.1. I need the square root of that. So X equals 7.45 times 10 to the negative 6. That X is my hydronium concentration, so I can take the negative log of that, and that's going to give me my pH. 5 point, how many sig figs can I keep? 2, so 5.1. All right, very similar question to the question before it. If you didn't get the first one, hopefully you evaluated where you got stuck and you got this second one. That's what it's all about, right? Growth. All right. Last one. So good time to pause it, see how far you get, come back, and we'll do this together. Okay, so again, they want the pH, meaning ultimately we need an H plus concentration or hydroxide. They give you an amount of an ACl solution and they give you a Ka value for this complex ion. So ACl3, when it dissolves in water, it's a soluble salt, and so it's going to dissolve into Al3 plus and Cl minus. Now Cl minus we just talked about, it's the conjugate of HCl, which is a strong acid, making it a useless base. Now AlC3 plus is going to complex with water and turn into this beast, which in this problem, they give you a hint that that's going to happen by giving you the Ka value of it. And as we can see, that's a weak acid. So we're going to write our equation for this. Oh, water is not charged. So it gives up a hydrogen, meaning that we have lost. My goodness, apparently I can't talk and write at the same time. Okay, we've lost a water. I now only have 5 because I pulled the hydrogen off of one, and that thing now is a hydroxide. Since I lost an H+, this is now a 2+. So I've set up my equation now. We talked about this before. If your acid is messy and you don't have time to deal with it, just write HA goes to H and A minus, right? And then you can just plug your numbers in directly. 0.01, 0, 0, and you don't actually have to mess with what that acid is. You can just skip that whole process. They don't ask you what that acid is. Just skip it. Go to the ice chart, right? Write the generalized equation. If they don't ask you for information, don't provide it. Not always a great life principle, but a great chemistry testing principle, right? Okay, now we're at our Ka, and they give that to us. I can write my Ka equation, and again, I can just use the general format instead of using that anion that is kind of bulky. And then I'm going to take my equilibrium positions, and this is looking super familiar. I'm going to ignore any x that is added or subtracted. Okay, we're ready to solve for x. Okay, Ka times 0.01 square root. My x is 3.74 times 10 to the 1, 2, 3, 4th, negative 4th. And this x is my hydronium concentration. So when I negative log it, I get a pH, which is equal to 3 point, how many sig figs? 4. Okay, again, the acid was a little scary, but the calculation's all the same, right? Or I guess the salt was a little bit complicated. Okay, so when you're dealing with salts, you just have one additional step, right? Your one additional step is to evaluate which of these is actually going to affect the solution, and then figuring out a functional way to write that thing that's going to affect the pH of your solution into a reaction. All right. Predict whether each of these will give you an acid, a base, or a neutral solution. So go ahead and make a prediction, and then we'll do this together. All right. A contains NH4+, which is a weak acid. C2H3O2-, which is a weak base, conjugate of acetic acid, right? So will it be acidic, basic, or neutral? We don't really know because they are present in equal concentration, right? But are they equal strength of acids and bases? you'd have to have the K equation. Now, if you have those K equations memorized, you can actually answer that question. Or you can go look them up. But for now, we'll have to say we don't know. If they're equal strength, it'll be neutral. If they're not equal strength, it'll fall to the one that's stronger. Okay, B. NH4, that's a weak acid. Cn minus, conjugate of HCN, that's going to be a weak base. Again, similar question, right? Which one's stronger? I believe Cn minus is a stronger base than NH4 is as an acid. But again, we need the K equations. We need to go look those up in order to figure it out. Okay, C, we have the aluminum ion, which is going to turn into that complex we saw on the last page, and we know that's a weak acid. SO4, 2 minus, that is the conjugate of HSO4 minus. So this is going to be a weak base. Again, comes down to strength. On the last page, what was this one? It was like 10 to the negative 4th or negative 5th. This one is going to tend to be a really weak base because it's the second protonation, right? It's the weak base off the second protonation. So again, I don't know. We're definitely going to have acids and bases here in all three of these solutions, but you're going to have to look up the Ka equations to figure out which ones are stronger and which ones are weaker before you can actually tell me, is it going to be acidic, basic, or neutral? It'd be easier if some of those were conjugates of very strong species, and then we could say for sure whether it was going to be acidic, basic, or neutral. A good example of that would be the last two things, right? We had NH4Cl. We automatically know on NH4Cl that Cl minus is going to be a useless base, right? So that one would come out acidic. And then what was the example before that? I think it was NaF. So again, since Na is the conjugate of something very strong, it becomes a useless acid, and then your solution is going to be basic for sure. So when one of the ions is the conjugate of something very strong and you can negate it completely, then you can say for sure whether something's going to be acidic or basic. In these other cases, you would have to compare the Ks in order to make that claim. Okay, our last one is on structure. Again, time yourself for a minute and a half, pause it here, see if you can come up with the same answer that we do. Okay, so as you read through here, which identifies the stronger acid? Okay, so the difference in these structures, this chain is completely the same. So the difference is that second oxygen, and what we saw were the more oxygens you add, the more polarized this bond is going to be. So let's see if one of these answers talks about that. Okay, so B talks about the additional electronegative oxygen atom stabilizing the conjugate base, right? So the conjugate base would be everything but that hydrogen. Yeah, that would make sense. Okay, B is your answer.